Damn it, why are these ODEs so hard to understand? Like, how do these numbers even describe physical events? It looks like just nonsense to me. Hey, have you heard of the mass spring simulator? No, what's that? It's this cool program that you can download and run to help you understand how an ODE actually connects to the physical world. It's really helpful. You should definitely check it out. That's cool. Can I get it on my computer? Yeah, you can download it from the internet. You can also watch this cool video that shows how the program works, how to run it, how accurate it is, stuff like that. It's really interesting. Oh, it's awesome. I'll definitely check that out. Thanks. Yeah, no problem.
This is the interface for the mass spring simulator. It's a program that allows you to enter parameters for a mass spring system and see how these parameters affect the physical actions on the system. It's a great tool for beginners to differential equations to help them visualize and connect the math to a real-world application. In this main user interface, you can modify various parameters like spring stiffness, damping coefficients, and even the number and orientation of springs. You can also modify the forcing function of the system here by typing in an expression in terms of t. Alternatively, you can select these options to set up a system with preset parameters to observe resonance or interference. After you've entered all your desired parameters, you can select this button at the bottom to plot the response of the system, that is, the position of the mass with respect to time, to give a quick and accurate depiction of the mass's behavior. However, most beginners don't want to just see math equations and graphs, so you can also run a physical simulation of the response by clicking this button instead. Now let's do a quick example. Let's say we want to add a spring of stiffness 4 newtons per meter in parallel with a series of springs, say with stiffness 10 and 20 newtons per meter. The mass is 2 kilograms and the damping is 1 kilogram per second. The default initial position of 2 meters is fine. Okay, let's plot it. Since the oscillations appear to keep happening beyond 10 seconds, let's change the length of simulation to 20 seconds instead. And since this might be a bit tedious to watch, let's also increase the speed of simulation to the max of 150% real time. Let's also add a forcing function in here, maybe simple t. This looks like an interesting plot. Let's simulate it. Notice how the program displays both the parallel spring and the set of series springs, and how the series springs appear to stretch proportionally based on their stiffnesses.
The numerical method used to solve the user-entered ODEs is the midpoint method, which will now be discussed.
You can see the mathematical representation of the midpoint method on the screen. Here, x is defined to be the position of the object, and we define a new variable, v, to be equal to x prime, or the velocity at that point. Using these definitions, it is possible to determine estimates of the velocity and acceleration at the midpoint between the current time and the next time. These equations are shown here as kv2 and kx2 respectively. Knowing these values, it is possible to make a good estimate of the next value of the function by taking into consideration both the initial as well as the intermediate values for both acceleration and velocity, and using them as the slope of the function. As shown in this illustration, using the slope at the midpoint can lead to a significantly better approximation of the next value of the function than by simply taking the slope at the current point. Looking at the code, you can see this is exactly the same process that is being used under the hood of the mass spring simulator. The expressions shown on the right map directly to the variables with the same names. Just be aware that y is being used to denote position in the code instead of x, and that an extra line is used to properly handle the forcing function.
Euler's method was also considered and initially implemented for this program. Euler's method uses the slope at the current time step to solve directly for the value of the function at the next time step. Actually, midpoint method uses Euler's method to find the value of the midpoint between the two time steps. So midpoint method is really just an improved version of Euler's method. A couple different cases were simulated using both Euler's and midpoint method to demonstrate the drastic difference in error between the methods. The error was measured as absolute because when doing relative error, any small difference in the absolute error around a position of 0 would cause large spikes, which we decided did not represent the error well at all. Here we can see from the first ODE that this system has a relatively low stiffness to mass ratio of 3.33. Therefore, it won't be oscillating too quickly. From the first plot, using midpoint method, you can't even see that this is actually two plots overlaying each other. There's actually the analytical plot as well as the approximate plot on top of each other there, but they're basically overlying each other perfectly. The accuracy is very good with very small absolute error. Its maximum absolute error is 10 to the negative 4 centimeters, and its average error is about 9 times 10 to the negative 6 centimeters over a span of 10 seconds. Basically nothing at all. However, for the same system, the plot of Euler's method also overlays the analytical solution seemingly perfectly. The error here is clearly larger than the midpoint method, about 3 to 4 orders of magnitude more, but still these results would be deemed acceptable for the purpose of this software. And since Euler's method requires less calculations per iteration, half the calculations, it might seem like a good choice. Where the difference is really noticeable is when the stiffness to mass ratio is very high, producing fast oscillations, such as this case. Here you can see that the midpoint method still approximates this curve fairly well. In fact, it's actually much more accurate than it looks. The reason midpoint method solution seems pretty choppy is because we aren't plotting every point calculated. Due to the limitations of the graphics software, we only take a certain number of points. In this case, for a simulation at 100% speed, which basically means 1 second of simulation is 1 second in real time, we only sample 1,000 points of the thousands more that were calculated. Shown below is the same system solved with the midpoint method, but at a speed of 5%. To achieve a speed of 5%, many more points were needed to be sampled to slow down the simulation. This gives a much smoother plot and shows that the midpoint method produces a very good fit. For Euler's method, you can see that the error is huge, and the max error is almost 1 meter. Again, it looks choppy due to the data sampling rate, but even at 5% simulation speed with a smoother curve, it's blatantly obvious how bad Euler's method is in this case. It could be improved by decreasing the time step, but this would increase the computation time exponentially and completely drown out the advantage that Euler has over midpoint in that it has half the calculations per iteration. To see how much of a difference this is, here's a simulation of the system solved by the midpoint method.
Get the simulation going. And that's pretty quick.
And here's the same simulation, but solved with Euler's method at the same time interval.
Already you can see it's quite long.
Clearly, midpoint method settled much faster than Euler's, and based on the error analysis we just went through, it is a much better approximation of the solution to the system.
Since the results of the midpoint method approximations are so close to that of the analytical solutions, this program can be used confidently for educational purposes to help demonstrate mass spring systems. Built-in resonance and interference features can help showcase important engineering concepts. By modifying the speed settings of the program, it becomes possible to see systems that would normally be too quick to observe. For example, this system over here oscillates approximately 20 times in the first second. You would normally be unable to see this, but by reducing the speed down to its lowest setting, it becomes possible to see each oscillation. With some changes to the software layout, this program could be made more general to analyze the response of other second-order systems, as the math would not change. To achieve an optimal computational speed to accuracy ratio, improvements could be made to allow the software to adjust the time interval as necessary. That is, it should know what the maximum allowable error is and set the time interval for the algorithm to be just low enough to achieve this error, thereby maximizing its computational efficiency.
Alright, I finally understand how these systems work. Yeah, I finished earlier than I thought, so I guess I can just do some relaxing and finish watching my movie here. Oh man, thank God for the mass spring simulator.